Hello guys, in this lecture we're going to continue our work and today we're going to cover differential kinematics. As we all know, if we were to calculate the inverse kinematics of a, let's say a 2-degree freedom robot, in this case, we would have the coordinate of the end effector, and the goal of the inverse kinematics is to calculate theta 1 and theta 2, right? And in this example that we had last time, we used inverse kinematics, and what we did is we solved theta 1 as inverse kinematics, as basically inverse tangent of ye over xe minus inverse tangent minus 1 of L2 sine theta 2 and divide that by L1 plus L2 cosine theta 2. And we had solved theta 2 um, based on the geometry of this, and we said theta 2 was equal to inverse cosine of xe squared plus ye squared minus L1 squared minus L2 squared, and this whole thing was divided by 2L1 multiplied by L2, and we know that the link length here is L1 and the link length here is L2, right? So once you have XE and YE, you can calculate theta 2, and after you calculate theta 2, you can replace it in this equation, and you can calculate theta 1 primarily based on XE and YE. So sometimes the geometry of the robot will actually make it very difficult to obtain this closed form solution, right? So this is referred to as a closed form solution, and this is not always feasible. So instead, what we can do is we can actually apply differential kinematics, and we are going to be able to find theta 1 and theta 2 based on XE and YE without actually having to figure out all the geometry. And the approach is actually pretty straightforward. So what we'll do is we will use forward kinematics, we'll differentiate forward kinematics, and we can obtain a relationship between dx and d theta, right? So let's see how that is actually implemented. So what I'll do is I can begin by writing xe, right? So the forward kinematics of this robot is going to be, I need to be able to represent xe and ye in terms of theta 1 and theta 2, right? So what is xe? In this case, it's going to be L1 cosine theta 1 plus L2 cosine theta 1 plus theta 2, because we know theta 2 is only relative to theta 1. So here we have theta 1. So if I was basically projecting that, obviously it has to be cosine of theta 1 plus theta 2. And how about ye? Ye is going to be equal to L1 sine theta 1 plus L2 sine of theta 1 plus theta 2. All right, so obviously the goal is to actually solve theta 1. And as you can see, this is a highly nonlinear equation, and it's very hard to basically pull theta 1 and then from this to be able to solve it. So what we can do actually, we can differentiate this guy. And by differentiating that, we can actually obtain a relationship between theta 1 and theta 2. So what is, so xe is a function of theta 1 and theta 2, so it's a multivariable function. And if I were to differentiate the xe, I'm going to have to do this, right? I'm going to have to do the xe, partial derivative of the xe relative to theta 1, multiply this guy by theta 1, right? Plus the partial derivative of xe with respect to theta 2 multiplied by the theta 2. All right, and I'm going to do the same thing on ye. So what is dy? Dy is going to be equal to, again, partial derivative of dy with respect to theta 1, because ye is also a multivariable function of theta 1 and theta 2. So d theta 1 plus dy d theta 2 multiplied by d theta 2. So if you actually look close here, you can see that we can basically put this as a matrix operation, right? Because you have, theta one basically um, is applied here and here, and theta two is applied here and here. I can actually rewrite that as a matrix format, dxe dye, right? And I can actually put it like that, right? So I can put d theta one here, d theta two here, right? So these two guys, right, are being moved like that, right? So or this is coming like that, right? And then this is coming like that here. So I can write it like that, dxe d theta one, right? And then I have dxe d theta two, and then here I have qie d theta one, and here I have qie d theta two, right? So now I can actually, to summarize this, I can actually write this guy as dx, right? I can write this as dx is equal to, so this guy basically is actually called the Jacobian. So this is a Jacobian of the robot and it's referred to as J, all right? So dx is equal to J d theta. And this Jacobian matrix actually allows me to relate any small variations of theta to any Cartesian variation of the robot, right? So we know J is going to be a function of what? J is actually a function of theta 1 and theta 2, right? Why? Because xe and ye are both functions of theta 1 and theta 2, so J is a function of theta 1 and theta 2. So for any given pose of the robot, or for any given, for any given values of theta 1 and theta 2, right? If I can calculate a J, and I can calculate if, thetas move by, this guy moved by 1 degree, and then this guy moved by, minus 1 degree, I can actually relate dx. All right. We're going to do actually an example now very quickly, but what is also very important here to have is, so now we can basically relate, small movements in the Cartesian into small movement in, the joint space of the robot, right? The joint space is where the thetas are existing, and then these are vectors, right? So dx is, x, y. If you have, more than 2 degrees of freedom, it would be x, y, z. Your patrol, for example, ultimately, in this course, we're not going to be dealing with that, so we're doing mostly 2 or 3 degrees of freedom robots. What I can actually do is I can now differentiate with respect to dt, right? So if you divide by dt on both ends, what do you end up with? So this is actually the velocity, right? So the Jacobian also relates the velocities, and then what is d theta dt is your angular velocity vector, right? Well, what is v? V is actually equal to what? Is equal to vx vy, right? So here we are dealing with vectors. J, what is your omega here? It is omega 1 and omega 2. So if I actually, so back to my previous robot, this is what I had. So what is the Jacobian doing basically? The Jacobian actually is rating, this is the x velocity of an effector. This is your y velocity of an effector. This is omega 1. And then this is omega 2. Remember, omega 2 is not absolute, right? Omega 2 is only relative to omega 1. If you want to get the net velocity of this link, like the angular rotation of this link, you have to basically sum omega 1 and omega 2. Okay, so this is a very important relationship that Jacobian establishes between the Cartesian velocities of the end effector and the rotational velocities of the various joints along the robot. Okay, what I would actually like to do now is let's actually go ahead and then solve the Jacobian and then continue to work on the Jacobian. And we said the Jacobian is going to be provided to us as well as dxe d theta 1, dxe d theta 2, and dye d theta 1 and dye d d theta 2. Okay, how do I calculate dxe d theta 1? So let's do it here. So dxe d theta 1 is going to be equal to, well, I'll quickly rewrite what was xe. So xe was equal to L1 cosine theta 1 plus L2 cosine theta 1 plus theta 2. So dxe d theta 1, basically, you are doing the partial derivative of xe with respect to theta 1, right? So this guy is going to be minus L1 sine theta 1, and then here minus L2 sine theta 1 plus theta 2, right? How about dxe d theta 2? Well, this guy is going to be 0. This guy is going to be equal to what? Minus L2 sine theta 1 plus theta 2. Now let's continue here. So what was, so we need to get dy e theta 1. So we recall ye was equal to L1 sine theta 1 plus L2 sine theta 1 plus theta 2. So we need to capture dye in terms of d theta 1. So it will be L1 cosine theta 1 plus L2 cosine of theta 1 plus theta 2. And then the last term that we are calculating is going to be equal to dye theta 2, which is equal to what? L2 cosine of theta 1 plus theta 2. So the Jacobian for this 2 degree of freedom robot is given to you as what? First entry is dxe d theta 1, which is equal to minus L1. So I'm going to do sine theta 1 as simply S1 minus L2 S12. Okay, now dxe d theta 2 is equal to minus L2 S12, which is sine of theta 1 plus theta 2. The second row is dye d theta 1, which is equal to L1 C1 plus L2 C12. And then I have dye d theta 2, which is equal to L2 C12. So now you can see basically the Jacobian is a 2 by 2 matrix in this case. And the reason why it's 2 by 2, it's because it's a 2 degree of freedom robot, right? It's a 2 degree of freedom robot and it's operating in a Cartesian space, right? It's operating in a 2D space. That is why this guy is a 2 by 2. We'll actually go more into this as we go later in the course. But you know, this is a Jacobian, and you know the Jacobian is actually a function of J is a function of theta 1 and theta 2, right? It's not a function of xe or ye. So now back to my relationship, I know that dx is going to be actually equal to j d theta. I can actually now solve d theta, which is the inverse of this Jacobian matrix multiplied by dx. Okay, so now I can also relate a change in the x with respect to a small change in d theta. Now I can actually use this to be able to solve the inverse kinematics of the robot. And the way that we will actually do this is based on that, right? So let's say you have, you know, this is your robot. So what I can do now is I can actually use my previous relationship to iteratively solve for, you know, the inverse kinematics of the robot, right? But that would be done basically iteratively. So let's say the robot is initially at at a particular position, right? XO, which is given to me as X0, Y0, right? And now I would like to actually take the robot to, you know, I want to do the inverse kinematics of the robot at this position, right? And I'm actually going to refer this to xg, x of the goal, and again, x of the goal basically as, you know, xg, yg, Okay. So here's what I can do. Okay, so I can now iteratively actually use differential kinematics to be able to solve this problem. And here's what we'll do. So we know that the theta, right, small changes in the robot joints is related by the inverse of the Jacobian with respect to dx, correct? So if I know basically if the robot is here and if this end effector, let's say the robot is at this point x0 basically, right? I cannot actually solve theta, what theta 1 and theta 2 are for this, but I can actually solve if x0 moves by a little bit, so you know x0 plus del dx, and if y0 is moved by y0 plus dy, right? I can do this subtraction like dx and dy from this point, and I can multiply this by the inverse of the Jacobian, right, for these angles, and then I can actually solve for how much these joints have actually moved. So I know that theta 1 has moved by d theta 1, and I know that theta 2 has moved by d theta 2, right? To be able to work with a Jacobian, actually always need to actually have the angles of the robot. So here is what we will do, and here basically you will have the angle iteratively. So you need to know the initial theta 0, here theta 1 and theta 2. So you would need to actually know that, and you use your forward kinematics to be able to calculate the initial position of the robot. But the solution actually is all developed here in the joint space. Okay, so we always actually have to have that. So let's say we're starting from a random position, theta 1 and theta 2, and then we are trying to actually solve the inverse kinematics. We are trying to solve, you know, what are theta 1 and theta 2 when the end effector is at xg. Okay, so again, here's the problem that we're solving, right? What are the values of theta 1 and theta 2 when the robot is at xg? And what we do know, we only know the initial positions or the initial joints positions of theta 1 and theta 2 at some random position. At that random position, I'm actually able to obtain the x0 of the robot based on forward kinematics, right? Forward kinematics mean, you know, what is x1 here, right? What is x0? X0 is equal to L1 cosine theta 1 plus L2 cosine theta 1 plus theta 2. And I know y0 is going to be equal to L1 sine theta 1 plus L2 sine theta 1 plus theta 2, right? Okay, deal. So here's what I'm going to do. So d theta is actually equal to what? Is equal to theta I plus 1 minus theta I, because we're doing this iteratively, right? Is equal to j minus 1. What is dx? So dx is basically I'm starting at this x0 and I'm actually going to this goal position, right? But I'm not going to take this whole thing as one time because it will be a very large dx. We want to take a very small amount of dx. So we have to actually multiply this by value alpha, where alpha is, you know, much less than 1. Okay, usually, you know, could be like, you know, 0.01. Okay, so now we're basically multiplying this whole distance by this alpha to be able to reduce this guy, right? So it's going to be, what is my dx now? Dx is my x goal minus my x0, right? X0 is the current position of the robot. Yeah. So now I can actually write, so I know my initial thetas, right? I know j is a function of my theta. I can actually now solve for my next theta. So this is my theta I plus 1 is equal to theta I plus inverse Jacobian alpha x goal minus x0, right? So you do that in a loop and you continuously repeat that until your error becomes 0, right? So every iteration basically you update your x0, right? Every iteration you update your x0 and the error is reduced. Ultimately, theta I will actually convert to one value where you are actually solving the inverse kinematics of xg. Okay, how do you get x0? X0 is your forward kinematics, right? And we know what forward kinematics is by now. It's forward kinematics of your whatever theta I you have, right? So as you move the robot, basically update your position. Does that make sense? What is xg is given to you, right? So this is given. Okay. What is j? J is actually a function of, let me just setup here. J is a function of theta I, right? Theta I as a vector, right? So is a function of theta 1 and theta 2, which you actually have it here, theta I. So every time you update your theta, you compute your Jacobian, you update your position, and you find your next theta. And next iteration, you use this theta here, and use this theta here, right? So always you are using the older theta to calculate your Jacobian, to update your position, and you add this increment to your older theta, okay? So I want to give you guys obviously some examples on that, and I think the best way to learn is by really doing. So this is how you can do the inverse kinematics of a robot using Jacobians. Let me quickly share my slide, and here I can show that to you guys here. So this is on our notes. So this is differential kinematics is, you know, x is equal to a function of theta. This is forward kinematics, right? And when we try to find the q or the angle as a function of x, it would be inverse kinematics. Solving inverse kinematics from geometry is very difficult sometimes. So what you can do is to actually use differential kinematics. So instead of trying to obtain solving this nonlinear problem of q is equal to some g function of x or f minus 1 of x, you can simply differentiate forward kinematics, which is very simple. So there is always a derivative for your forward kinematics, right? The derivative of the forward kinematics will simply relate small displacements in the joints to small displacements in the end effector. All right, so this is a very basic example that I have here. All right, so if I have a 1 degree of freedom system, so I simply have this bar, and I have the angle theta. The forward kinematics is basically I'm locating this position, the end effector position, as a function of q, right? So what is the coordinate of the end effector? It will be L cosine q, right? If q is greater than 90 degrees, then obviously cosine of an angle that is greater than 90 will actually be negative. So this is my x, it's always valid. Obviously, if I want to do the quick inverse kinematic solution, what would that be? So we know here, as inverse kinematics, we know x equal to L cosine of q. Inverse kinematics, you are trying to find q as a function of x. So q is going to be equal to what? X over L, and you are doing the inverse cosine of that, right? It's very simple. But what if you aren't able to see that, right? What you can do is you can do differential kinematics, and you said what you do is you can differentiate dx with respect to theta or dq here. So dx is equal to minus L sine q dq, right? So dq is equal to minus 1 L sine q. So this is basically like the Jacobian, right, applied on a 1 degree of freedom system. So how can we solve this problem, right? Obviously, answer 1 is you do simply the basic inverse kinematics, but answer 2 is you start with a random, position. You start with q0, where the bar is currently at. If you have a robot, you can pull the encoders, right? You know where the robot is. Based on the encoders, you can find the position based on the forward kinematics model. Then you want to move the robot to a particular point xg, right? So what is your dx now? Dx is equal to, you want to take a very small step, right? So x goal minus your current position. Once you have dx, you can find the dq, right? So what should be the change in the angle that would actually lead you to close down on the error between where you are and where you want to go. And then you keep doing that, right? If you keep doing that, ultimately q will stop changing, and then dq will actually go to 0 because your dx will actually converge to 0. Okay, if you want to visualize that as a visually, so you have a goal position, right? This is your current position. This is your x goal minus x. So this is the x. So this should be actually a minus. I believe this should be a minus for sure. X goal minus current position. So this is your dx. You multiply it by at the inverse of the Jacobian here, right here. It's mapped on 1 degree of freedom. So we have the dq. So remember, dx multiplied by the inverse Jacobian will actually give you dq, right? So this is your change in q, but you also have to add that to the change in position, to the current theta, right? So d theta plus theta will actually give you the latest theta, right? So now we actually have a position where you want to send the robot to. So now you can feed that into your, for example, a PID controller or whatever you're doing to actually set the position on the actual hardware. Okay. This is the loop. So again, this actually has to be minus on one fifth side. So xt minus x, right, will give you dx. Dx multiplied by inverse j will actually give you change in theta, right? And then change in theta will always actually be added to your current theta. So what is that? This is your FK model. Right? FK model will take the joint position from sensor, for example. Your joint position, fit them into your FK model. Right? FK model will return your actual Cartesian position on the robot, right? And then XG is where you actually want to take the robot to, where you are trying to command the robot to go to. Okay, that is that. So on a 2 degree of freedom robot, so this is actually what we had earlier. So this is a 2 degree of freedom robot. We know how we got that, right? So you get that by differentiating the forward kinematics with respect to theta 1 and then theta 2 here, right? This is your X and then this is along your Y road, right? Okay. Uh, so dq is equal to the inverse of Jacobian. So this is my inverse Jacobian. This is my forward kinematics. So q, you feed that into your forward kinematics, you obtain your x position. This is your desired minus existing position will give you the error, right? You still have to multiply this by alpha because here we're doing this on we're moving the robot by very tiny amounts, right? We're not moving the whole thing at a time. So that is why you actually have to have an alpha here that is very small, and you multiply this by the inverse of the Jacobian, you get how much you should change theta by, but you still have to, that change of theta is relative to your current joint positions. So you still have to add that to your current joint position, and then you would actually be able to do that. Okay, guys, so if you apply this on a 2 degrees of freedom robot, if you have X, Y, Z, again, you are also able to do that in a very nice and simple way. Yep, so if you differentiate by dt, as I did earlier, right, so we know dx is equal to j d theta. If I derive, if I differentiate by dt, if I divide this guy by dt and then this guy by dt, right, I will actually be able to relate the joint velocities, right? So which is q prime with end effector velocity. Sometimes end effector velocity is referred to as twist, but I personally like to call it simply end effector velocity, so this guy is a vector which contains vx, vy, and vz, and q prime actually contains omega 1, omega 2, and omega 3. Okay, guys, so that is it regarding Jacobians, and next time we'll continue more with Jacobians. Any questions, guys? Please do not do not hesitate to contact me by email. I'd be extremely happy to set up, at any time a one-on-one meeting, or like I said earlier, I keep an open policy in terms of office hours. So any questions you have regarding the course, I'll be more than happy to jump on a call with you and address any questions that you actually may have on the course.